So let me explain why orthogonal bases are better. It turns out that given an orthogonal basis u1, u2, uk of some subspace, and again we're dealing with Rn in here, it turns out that the coordinates of any vector x of s are given by this fairly simple formula. The coefficient or coordinate ai is going to be given simply by the dot product of x and ui, the same I, divided by ui dot ui. Now that formula may and should sound and look familiar. We have seen it before, and we're going to come back to revealing what it is. But for now, just notice that it is a fairly simple formula. It does not require solving a lengthy linear system. So this by itself tells us that using orthogonal bases has an advantage. But let me prove you why that is so. Okay, I'm just making this claim. But how do I know that that's true? Well, let's say that I have a vector x, and I know that this is a linear combination of u1, u2, uk. Remember, our purpose is to find out what the coefficients a1, a2, ak are. So let me take the dot product of x with any one of those ui, those basis vectors. Well, by definition, this is going to be the dot product of the whole linear combination with ui. But we know that the dot product is distributive. So that product on the right hand side can be written as a1 times u1 times ui plus a2 times u2 times ui, etc. But now remember, these basis vectors now are orthogonal to each other, which means that all those products are dot products are going to be 0 except for only one, namely the ith product. So what we're going to be left with is just ai times ui dot ui. And from that, of course, all I need to do is just rearrange things to find out that ai is going to be equal to x dot ui divided by ui dot ui as I had claimed. So once again, this already gives us a simplification with respect to finding these coordinates, but let's give some meaning. What does this formula mean? So we're trying to give some meaning to this formula that we have found out. So what we have found out is that a1 is going to be equal to the corresponding formula with u1, and a2 is going to be given by the corresponding formula with u2, etc. up to the last one. Now, hopefully, you will remember what each one of those terms actually is. If you look at the first term, what that is actually the projection of x on u1. And similarly, the second one is the projection of x on u2, and all the way through to the last one. So what we have is that if a basis is orthogonal, then basically x can be written as the sum of the projections of x itself onto each one of the vectors. And you may recall that this is very similar to what we were doing with orthogonal complements. We ended up being able to write each vector of the vector space as a sum of one vector in one subspace plus another vector in its orthogonal complement. The trick there also was that the two subspaces were orthogonal. Here all the ui's are orthogonal to each other, and therefore this generalization also holds. Visually, what are we talking about? Well, what we're saying is, let's say that we have a basis consisting of u1, u2, u3, and let's assume that these three are actually perpendicular to each other. They don't have to be of unit length, remember, they don't have to be I, j, k, the usual ones. They just have to be three vectors which are orthogonal to each other. Now, if I take any other vector x, what I can do is I can obtain x by considering the projection of x onto u1, so that'll be the first piece, and then the projection of x over u2, and then the projection of x over onto u3. Add up those three projections, and that will give me back my x. So again, it's something that you may find quite or feel quite familiar, because that's what we have usually done up to now, except that now we're generalizing it to any basis as long as the vectors are orthogonal. What about if they're also normal? Turns out that when we have an orthonormal basis, that is actually best also from the algebraic point of view. Okay, so it turns out that in fact, given an orthonormal basis u1, u2, uk, so this time those vectors not only are orthogonal to each other, but they're also of unit length. And again, we're talking about vectors in some Euclidean space Rn. Then the coordinates of any vector x of s in this given basis are given simply by ai equal x dot ui. So that there we have an even simpler formula, okay? And that's one other reason why these orthonormal bases are actually very good. It's very easy to find these coordinates, so it's very easy to figure out what each vector, how to obtain each vector in terms of a linear combination of the basis vectors. The proof here is very, very easy. Well, if it's an orthonormal basis, then it's got to be orthogonal. So that means we already know that the AIs are given by the formula we just constructed. But remember, in this situation, these vectors are not only orthogonal, they're also normal, meaning that they're unit vectors. So that means that ui dotted with ui is going to be equal to 1. And so that leads straight to the answer. Okay, so that's all there is to it.